Good morning, guys. Today I'm going to do the Zener Diode. We're going to look at its properties, how it works, and everything else. First of all, let's look at the symbol of a Zener Diode. This is how it looks like. You will notice already it is different from a normal diode. It has this hanging next to it to represent the Z in the Zener. So this still remains the cathode and that still remains the anode. The operation of a Zener diode, different from a normal diode, is that this one is a regulator. It's used mostly as a regulator. Okay, as compared to a normal diode which we use to rectify. So as a regulator, this one ensures that the output of your voltage in a power supply or in an application where it is used is maintained at a constant voltage. So briefly, if you would remember, our power supply consisted of 3 block diagrams which we did. Here we have the rectifier and here we have the filter. So this is where your Zener diode would fit as a regulator. Alright. So going back to the Zener diode, when we look at how it operates in the reverse bias section of your graph of a diode. So here will be your forward bias and here will be the Zener diode. Let me correct that. Alright, more or less like that. So this area here is where your Zener diode operates, in this reverse biased area. What is of importance is that the current there must be a certain minimum and a certain maximum for a Zener to operate properly. And which are those current? We have here what we call IZK. And a little bit down here we have what we call IZM. This is the area in which your Zener diode operates. So the minimum current through the Zener for it to maintain regulation must be IZK. And the maximum current for a Zener to operate and maintain regulation must be IZM. So when you have your circuit, a Zener is connected and it operates in the reverse bias situation. That's your Zener diode in a circuit, and then parallel to it will be your load, RL. So if this is your total current, IT, at that point, some of that IT is going to go there and some of it will go here. It'll go that way. So this one we shall call it IRL, and over here we have IZ. So the Zener current that's going to go here must not be less than IZK or IZM. And for as long as we have minimum current of IZK and maximum current of IZM, this Zener will maintain regulation, meaning the voltage here on the output will be a constant voltage. I hope that is clear. Now, let's look at the equivalent circuit of a Zener diode. If we look at the symbol of a Zener diode, this is what we have. An equivalent circuit of a Zener diode is this one here, which represents an ideal situation. It's an ideal one, where you have this in a form of VZ. And in an ideal situation, your graphical representation thereof would be that of a ideal situation like that. But if you take it further and you do the practical one, your graphical representation of a Zener will be in this format here. So this one represents the most practical and complete form of a Zener diode. The resistor here, which is our impedance, is ZZ. And here now we have VZT. And our current flowing through here is IZT. I'll get back to that in a graph for that. So the total voltage that we can get out of that will be VZT plus VZZ. So if we look at how that works, and going back to that graph again, here we have our graph. Okay, and like I said, this one over here is IZK, and over here we have IZM, but this one here is IZT, which is our operational current inside the Zener diode when there is no change at all. So you will see now, because I mentioned that the current must not be more than IZM or less than IZK inside the Zener diode. At any given time, the current, the voltage across the Zener diode, VZ, will be given as VZT specified at IZT plus VZZ, whereby in order to be able to get VZZ, we need ZZ multiplied by the change in current, IZ. The change in current, which we will get when we calculate, is most of the time IZT minus the current at which your Zener current has changed towards. So in other words, if IZT changed to 20 amps and it was given as 40 milliamps, then your change in current will be 40 milliamps minus 20 milliamps. Okay, and this will be our lesson for today. Thank you very much.